All right, so last time we ended with our proof of the second part of the fundamental theorem of calculus, which essentially says that in order to actually evaluate a definite integral, you can take its antiderivative and evaluate between the limits of integration. So go ahead and go back and rewatch all that for some kind of practical, intuitive explanations and then a little bit more formal, symbolic way to justify that. All right, so right now we're just going to continue, and this is really where we're now connecting all those antiderivative ideas, which may have seemed to have been forgotten from the end of the last chapter, with now actually evaluating some definite integrals here. So we did one last time. Let's continue. Let's look at another example here. So suppose we have our definite integral from 1 to 2 of 3x minus 2x squared plus x to the 5/2, all divided by x to the 3rd dx. Okay, so just like in our antiderivative section at the end of the last chapter, remember right now we have a very limited set of problems that we can take the antiderivatives of. Things that are term by term, x's to powers, or like e to the x we know, and we know a couple of other, or actually more than that, but we know some very specific trig antiderivatives and things of that nature. What we definitely can't do is take an antiderivative of a quotient by taking the antiderivative of the numerator divided by the antiderivative of the denominator. So in order to first find this antiderivative, we need to do the division. So we are going to divide each term, since I have just a monomial here in the denominator, we are going to divide each term in the numerator by that denominator. So we're going to have 3x divided by x cubed. So dividing, you can just subtract your exponents, so 3x to the negative second, minus, similarly, 2x to the negative first, and then plus we have x to the 5/2 minus 3, so 5/2 minus 6/2 would be a minus 1/2. So now we have it into a term by term situation, term by term, x's to powers. So now let's actually take this antiderivative. So notice the integral symbol stayed until we take the antiderivative, and now I will drop it. So antiderivative, we're applying our power rules. Constant multiples get carried along. So 3x to the add 1, we get -1 divided by that -1. Now, this is the time where, power rule works for everything except this one situation. If I find myself, and I may do this a time or two, -1 plus 1 is x to the 0, division by 0, that is my kind of red flag. Oh yeah, this is the one time, erase, 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 when I don't get to use the power rule. And so maybe it would have been easier to even think of, in this case, this second term, instead of as x to the -1, as a 1 over x. So the -2 gets carried along as a constant multiple, and then the function that we learned whose derivative was 1 over x was that natural log. But when we take the antiderivative, we do need natural log of the absolute value of x. And then plus last term power rule, so again add 1, so -1/2 plus 1 is a 1/2, and then dividing by that 1/2, which again, I want you to clean that up, and that'll be multiplication by 2. But I don't want to use the integral symbol, but I do need to remind myself I do still need to evaluate in between my limits of integration, so in between 1 and 2. So again, some instructors you might see even write it as x equals 1 and x equals 2, because those are x limits of integration. So now we're going to go ahead and kind of do some simplifying here. So again, this is your antiderivative, FYI, that is your capital F of x. And now we are going to sub in and evaluate f of 2 minus f of 1. I'm going to go right to kind of subbing in some of those values here. So we're going to have this negative, well, let's first rewrite. So this is like -3 over x. You could even rewrite, if you were so inclined, you could rewrite this second term, and you might see this done from time to time as like a natural log of x squared, and then the absolute value bars don't need to be there because squaring would already make it positive. And then the last term there, dividing by a half, is like multiplying by 2, so maybe 2 root x. So just maybe cleaning that up just a smidge there before we go to subbing in. So now again, you're subbing in capital F of 2 minus capital F of 1. Not that you have to write that out, let's just get right to it and do that. So we'd have our negative 3 halves minus natural log of 4 plus 2 square root of 2. So that's subbing in the upper limit of integration, minus subbing in the lower limit would be a minus 3. Minus natural log of 1, 1 squared is 1, but natural log of 1 is just 0, so I'm going to be able to drop that term. And then plus 2 times the square root of 1 is just 2. And so it looks like this whole second set of parentheses is really going to simplify down to a negative 1. Of course, minus that negative 1 is going to be plus 1. And so we're going to end up with, so when I have that minus the negative 1, that's going to change into plus 1. And so 1 minus the 3 halves is going to give me minus 1 half. So that's just from looking at now this 1 and the minus 3 halves. And this is really as good as I can get for an exact answer. Minus natural log of 4 plus 2 square root of 2. Or you could go to some sort of decimal approximation, but you need to be cautious if you're not asked for decimals. Most of the time we'll default to some sort of exact form like that. Okay, let's look at another example. So number 2, that was number 2, I guess. So let's look at another one here. So number 3, let's look at the definite integral from 0 to 1 of negative 3 over the square root of 1 minus x squared dx. All right, so this is one that we should know from a very specific list of previously learned derivatives. So thinking about the negative 3 getting carried along as a constant multiple, if we remember, the derivative of sine inverse was 1 over the square root of 1 minus x squared. So the integral, or the antiderivative of 1 over the square root of 1 minus x squared, is going to be sine inverse, or arcsine if you prefer, of x. And again, now evaluated between my limits of integration. And so we first sub in our upper limit first, so negative 3 sine inverse of 1 minus the negative 3 sine inverse of 0. So of course when you get it down to that, just minus the one term there that's negative, that is going to change into addition. So if we think about, where is sine 1? So that would be at our pi over 2, and then plus, thinking about where sine is 0, that's going to be at 0, and so you could use your calculator on that if you needed to double check, of course, but this ends up being negative 3 pi over 2. Okay, so this is just a nice chance even just to review some of those antiderivatives that we talked about at the end of the last chapter. So we're just using the second part of the fundamental theorem. Additionally, as we're going through these, so I'm writing out our fourth example here, kind of every time I should probably be verbally saying this is only possible, what we're doing with the second part of the fundamental theorem, if the function is continuous on the interval, closed interval from a to b, which, all of these have been, but it is something to kind of be mindful of there. All right, so let's look at another one. So the definite integral from 0 to 3 of 2e to the negative x times e to the 2x plus 3e to the x dx. All right, well, we cannot take the antiderivative of a product as the product of the antiderivatives. So I am forced to multiply this out, and at the same time am really hopeful that I get something that looks much simpler, because right now we don't know the antiderivatives of things like e to the 2x. The only antiderivative that we know is the antiderivative of just e to the plain old x. And so hopefully that's what we'll get down to, are some simpler looking things here. So distributing through the 2e to the negative x, we'd have 2e multiplying with the same base, you add your exponents, and nicely we do just get e to the x here. In the second term, we would have plus 6, and this one's even better because this would be like e to the 0, which is just 1, so that just leaves us with that factor, the coefficient rather, of 6. All right, so this, we can now take our antiderivative, and so when we do that, the antiderivative of e to the x is e to the x, 2 as a constant multiple gets carried along, and antiderivative of 6 is 6x. We have dropped our integral symbol, but of course we still need to evaluate in between our limits of integration. And so subbing in our upper limit first, 2e cubed plus our 6 times 3 would be 18, so it's that upper limit quantity minus subbing in the lower limit quantity. Well, 2e to the 0 is just a factor of 1 there. And then, of course, plus 6 times 0, well, that's just going to be 0, so that whole thing is gone. And so what do we really have here? We have 2e to the third plus 18 minus, and then that second set of parentheses was just minus 2. And so our final answer here looks like 2e cubed plus 16 in its exact form. All right, let's just do one more. So kind of our third example of this video, or maybe fourth example, but we're on number 5 in total. So number 5. Let's look at the definite integral from pi over 6 to pi over 3 of cosecant of x divided by tangent of x dx. All right, so can't take an antiderivative of a quotient with the quotient of the antiderivatives. In addition, I don't even know functions whose derivatives were, cosecants and things like that. So our only hope here is to do some simplifying, of course, just with some basic trig identities here. So let's see what we can do with that. So of course, cosecant, just using our quotient identity, is 1 over sine. Divided by tangent is like multiplying by cotangent, multiplying by the reciprocal of tangent. So dividing by sine over cosine would be like multiplying by cosine over our sine. Yeah, cosine over sine here. So that doesn't look, initially, I'll be honest, and I see where I'm headed with this, but for a second there I kind of paused because I was kind of thinking I was going to get some sines and cosines to reduce, I'll be honest. They don't. So what do I really have here? So I thought I was going to maybe get some things to reduce. I have cosine over sine squared, but that is not helpful at all. It's still a quotient, and we don't even know how to deal with things like sine squared, so that would not be helpful. But let's look at what's staring us right in the face at this point. So maybe some things reduce, or maybe they don't in this case. But now, as I look at what I have, 1 over sine, once again, is cosecant of x times cosine over sine, of course, is our, cotangent of x. And that, cosecant of x, cotangent of x, that is one of our very special 6 of the original functions whose derivatives we knew. We now know those antiderivatives. So you should be referring back to whatever section 4.8 when we talked about these antiderivatives. So the antiderivative of cosecant x cotangent x was negative cosecant of x. So remember, what's the derivative of cosecant? Negative, so those two negatives would go back to positive, cosecant of x cotangent of x, so that's correct. We drop the integral symbol, but we do still need to concern ourselves with subbing in between our limits of integration. And so let's just kind of go back to the interpretations here with this being sine in terms of evaluating with our unit circle. So cosecant is 1 over sine. So I'd have negative 1 over sine of pi over 3 minus, subbing in my lower limit of integration, negative 1 over sine of pi over 6. All right, in that second term, of course, that's going to change us into addition. And then the sine at pi over 3 is root 3 over 2. So we have 1 divided by negative 1 divided by root 3 over 2. We'll clean that up in a second. Plus, and now the sine at pi over 6, that's our 1/2. And so, what do I have here? I have negative 2 over the square root of 3 plus 2. And so you could certainly leave it that way. 2 minus 2 over the square root of 3, that's okay. If you prefer, you could multiply the first term by a root 3 over root 3 in order to get a common denominator. And then you could have 2 root 3 minus 2 over the square root of 3. If you really don't like the look of radicals in the denominator, you could multiply by the square root of 3 over itself. And then you would have had, in the first term, root 3 times root 3 would have been 3. 3 times 2 would have been 6 minus 2 square root of 3 over 3. So, any of those would be fine, at least with me. Those are all nice exact forms. All right, so let's take a look at just one more example here. I think we're going to end with a little application problem here. So I guess this is our number 6. I think I'll just go to the next page here. So number 6, suppose we have a bottle of soda at room temperature, and we'll say we're at a room temperature of 72 degrees Fahrenheit, is put in a refrigerator at 4 p.m. and its temperature, so its temperature is changing at a rate of negative 18 times 0.5 raised to the T power degrees Fahrenheit per hour. And so the first thing I want us to do is part A. I want us to find and interpret. And once we do that, then we could use this to answer other similar questions. Find and interpret the definite integral from 0 to 3 of this function, negative 18 times 0.5 times 0.5 or a half, whatever you prefer, to the T power dt. All right, so first let's find it. So we're finding our antiderivative here first of this definite integral. And so the negative 18 is going to get carried along as our constant multiple. So again, if you take a look back to the antiderivative rules that we wrote out at the end of section 4.8, the antiderivative of a base that is not e, so a base like a half, to the t power, is that base, a half, to the t power divided by the natural log of that base, so natural log of a half. If you work it backwards, if you remember the derivative of a half to the t would be a half to the t times natural log of a half, and then those natural log of halves would reduce, and it kind of checks out. But you might want to just look that one back up from the end of chapter 4. All right, so there's our antiderivative, and now we need to simply evaluate between our limits of integration. Okay, so subbing in the 3, we'd have negative 18 times this half to the third divided by the natural log of that half. And I could have just maybe pulled this negative 18 over natural log of half out in front of the whole thing as well. But I'll just leave it right where it is. So minus, again, negative 18 times a half to the 0 power divided by natural log of a half. All right, so subbing in the upper limit of integration minus, and then subbing in the lower limit of integration. All right, so in this case, I'm going to, especially for practical terms of the problem, certainly anything to the 0 power, this would have been 1. Certainly, subtracting this negative, I could have changed this term into addition. But really at some point, in terms of like interpreting this in a practical way, this is one I'd say we would definitely go to our calculator, which I did in advance. So this comes out to be approximately negative 22.7. Okay, so that's what we get. Okay, so that's evaluating it or finding it. Okay, now let's actually think about, well, what does that mean? What did I just find here? Okay, so let's think about this for a second. Let's say I called a function capital T, like my temperature function, the temperature of this bottle of soda. What we were given to start this negative 18 a half to the t power, this was how fast the function was changing. And whenever we're given that information, that really tells me, so the temperature is changing at a rate, that degrees Fahrenheit per hour, all that is revealing to me that this is the derivative of this temperature function, which I'm going to refer to as capital T. So that is the rate of change of that function. So what did I just find here? So what we just found was this. So we just found, so what we just did looked like the definite integral from 0 to 3, and it was the T prime, the rate of change of the temperature function in degrees Fahrenheit. And so once we did that, first we found that antiderivative capital T, and by the second part of the fundamental theorem of calculus, we evaluated in between the limits of the limits of integration. So we did a capital T of 3 minus a capital T of 0, and that is what got us this negative 22.7. So what this is this is the change in temperature from these 3 hours. And if 0 corresponds to 4 p.m., so if the time at 0 is 4 p.m., then 3 hours later, of course, would be 7 p.m. And so when we pull all of that information together, what did we find? We found that the let's say the temperature of this bottle of soda, it actually dropped because it came out to be negative. It dropped by approximately, because I've rounded this, this wasn't the exact answer, right? I rounded to 22.7. So it dropped by approximately 22.7 degrees Fahrenheit from 4 to 7 p.m. So from 4 p.m. to 7 p.m. So that's the interpretation. So this is again, really what this whole notion of the second part of the fundamental theorem says. It's giving us that, net change in the antiderivative function. So the net change in the temperature, because that's the antiderivative of the rate of change of temperature. So the net change in the temperature over that 4 p.m. to 7 p.m. So then let's just add one last little part to this. And in some ways, this could have maybe been the whole question, and then it would have required that we went back and kind of did part A first. So now suppose we were asked, what's the temperature? So what's the temperature of that bottle of soda at 7 p.m.? So if we were asked that question, we might want to first think about, well, what was the temperature drop? Now that I know what the temperature drop is, I can say to myself, okay, well, it's going to be whatever the initial temperature was, and then it's going to be minus the temperature change. I mean, really, it's this kind of, it's plus the temperature change, which is actually the change in temperature, which happens to be a negative because it does decrease. It got put in a refrigerator. I mean, it's really the change in temperature, but obviously it's cooling off, so it's this negative here. So it's this negative, the decrease of about 22.7 degrees that we have to apply to that initial temperature. So it was initially at about 72 degrees Fahrenheit, and it drops by 22.7 degrees. And so this is going to end us at, 49.3. So again, we're working off of a rounded answer in part A. So I'll say approximately equals that it's at about 49.3 degrees by 7 p.m. So again, even if that was the full question, like what's my temperature at 7 p.m., I would want to look at, well, what's that change in temperature? But then I have to essentially add on or start with the initial temperature and then look at that, in this case, temperature decrease.